Hello, everyone. In this lesson, I would like to give you guys some homework guide. As you have seen, there are other guides on homework in previous lessons. But on this one, I'm going to select some homework questions and continue to explain to you how to apply the definitions. And in other words, how to make your statements, how to say it. Okay. We start with this example. The first one, this is a homework question. From the graph of function f, state the numbers at which f is discontinuous and why. Discontinuous. So here we have the definition of function continuous at a point A. So to state it's discontinuous, we know there's three elements, right? So how do we say it? How do we say it? So here I'm going to start showing you how to say it. How do you write down the word to make your case and also make it relevant in the context of the topics? Okay, basically you're using the definitions and theories. For example, right, in this picture, I made a copy of this picture. You can see at point -4, you would say, right, at this point, this means that the function is not defined at -4. So the function is not defined at -4. So look at the first sentence, right? F is not defined at a point. If it's not defined, then it is not continuous. Okay, so this is how we're going to say it. F, okay, is not defined as a -4. Okay, thus F is not continuous at a -4. That's it. You're done. Okay, let's look at the second point. The second point, -2. Okay, the second point is -2. And we can obviously see that at -2, the function is defined. Okay, so we can, if you quote the first reason, right, f is the contrary to f is defined, certainly that's not powerful. So what will make it powerful to state that f is not continuous at -2? So from this picture, what can we tell? Well, f of -2 is defined. Okay, f of -2 is defined. F is defined at a -2. So the first condition is satisfied. And what else? Limit, right? Does the limit exist? So we look at the limit, right? When x is approaching, we look at the limit from left and we look at the limit from right. And we're going to see the following, right? So we're going to make the statement, okay? We're going to use the limit definition, all right? So on the limit definition, we'll say limit when x is approaching -2 from smaller, okay, from smaller, and that limit obviously exists, but that limit and the limit of if f is the function, if x approaching from 2 larger than -2, okay, so from larger than -2, so limit from left and limit from right are not the same. So this is not the same. Okay, we look at, so let me get the arrow. So when x is approaching -2 from smaller than -2 versus versus x is approaching -2 from larger than -2. Okay. These two limits are not the same because you can see these two dots are not the same. If these two are not the same, that means what? That means the limit of the function at -2 does not exist. Okay, without the left and right sign, this one does not exist. D and E. So the second condition is not satisfied. Excuse me. And thus, you would say the function is not continuous at -2. That's all you need to say. That's all you need to say. Okay, let me have to make it 2 lines. Okay, this is how much you have to say. Okay, but you're going to use a notation. Okay, you're going to use a notation to make your statement clear and concise. Okay, so that's at -2. At 0. At 0. How about at 0, right? So this is at -4. And this is at -2. This is at -2. And how about at 0? Is it continuous? Is it continuous at 0? Well, the function obviously is defined as 0, right? All 3 conditions are satisfied, right? So f of 0 is defined, limit from left and limit from right are the same, so limit exists, and the limit is the same as the function's value as 0. So at 0, it is continuous. This question is asking to state the numbers at which f is discontinuous. So at 0, it is continuous. So we don't need to work on that. Okay. So at 2, same thing. At 2 and -2, the points are the same. The only difference is that you just have to change. You just have to change it to be at 2. Okay, change it from -2 to 2. So it's discontinuous at 2. And what else? At 4. Discontinuous at 4. At 4. Discontinuous at 4, the reason is a little bit different because you can use that the limit does not exist, or which is obvious, but in this case, limit from right exists, right? So limit when x is approaching 4 from larger does exist. It exists. And it is also equals to the value of the function at 4. Okay, it equals to f of 4. But limit of the function when x is approaching 4 from smaller than 4 it's negative infinity. Okay, it's negative infinity. So these two are not the same. They're not the same. So you can also say that f is not continuous at 4. So these are the different ways you can say it's discontinuous. So you just go straight for the condition that violates the continuity. Okay, so let's look at the second question. The second question is asking, so each of the numbers stated in A, determine whether the function is continuous from right or from the left. Okay, so this will be interesting because we need to look at the definition of continuity from left or right. So here's the definition of continuous from right or continuous from left. So let's look at the -4. Let's look at -4. At a -4, okay, at a -4, the function is not defined at a -4. So in other words, we cannot apply the definition because for a equals to -4, you look at the definition, you cannot write f of -4. Okay, so at a -4, okay, you would say f is neither right continuous nor left continuous. Neither. Okay, because we cannot apply the definition. In other words, for the function to be left continuous or right continuous, the function has to be defined at the point. So at -4 is neither. Okay, so let's look at a -2. -2 will be a bit more interesting because at a -2, the limit from right and the limit from left are not the same for sure. Okay, we got that. However, the limit from left, right? The limit from left, right here, when x is approaching -4 from smaller than -4 is equal to f of a -2. Okay, when x is approaching -2 from smaller than -2, it is equal to the function's value at a -2. So continuous from left at A. So we can say f is left continuous at -2. Okay, so that's what we can say. Now, is it right continuous at A? No, it's not, because we know they're not the same, right? So now at a +2, let's see what happened at +2. At a +2, we know it's discontinuous, but the limit of the function when x is approaching 2 from larger than 2 is equal to the function's value at a +2. Okay, so by definition right here, we can say f is right continuous at a +2. Okay, so this is about left continuous, right continuous. Now, last but not least, at 4. Okay, at 4. At 4, what happens? We just stated, right? We pointed out earlier, right? because this is true, so the function is also right continuous, right? Because of this, the function is also right continuous at 4. It's right continuous at 4. Okay, so now I'm going to extend this question to talk about the intervals of continuity. Okay, because it looks like on this function, right, the function is continuous. Okay, so continuity on intervals. Intervals, right? We had the earlier statements, right? We're going to come back to it. How do we say about the continuity on intervals? Okay, so look at the intervals. All right, so at -4, because the function is neither continuous, right continuous nor left continuous, so we know that f is continuous and from -infinity to -4, not including -4. Okay, from this picture. So let's look at interval from -4 to -2. Okay, -4 to negative from -4 to +2, and we know that f of x is continuous. Okay, we know that -4 cannot be included, but on the other hand, it is left continuous on -4. Okay, it's left continuous at a -4. Okay, I'm going to bring this statement here. Okay, because f is left continuous at -4. So here we're going to write -4, but we're going to use bracket on the side of 4, on the side of -2. Okay, so I'm going to write it this way: parentheses, bracket, because f is left continuous at -4. All right, from -2 to +2. Okay, from -2 to +2. Okay, so we're going to put in here. You can see we have a left continuity at -2. We're going to put a bracket about -2. And next, we look at the interval from -2 to -2 to +2. Well, obviously the function is it's not continuous. There's only left continuity and right continuity at 2, right? Therefore, f is continuous from -2 to +2. So next, look at the interval from 2 to 4. Okay, so from 2 to 4, 2 to 4. 2 at 2 is right continuous. Okay, it's right continuous, but at 4, it's not continuous because linear does not exist. So this time the interval will be written this way. Okay, 2 is closed, 4 is open. And last but not least, f is continuous on the interval from 4 to infinity. And this time we're going to put a bracket. We're going to put a bracket at 4 because it is right continuous at 4 to +infinity. Okay, so this is the continuity on intervals that we are talking about. Okay, so right continuous, left continuous, when we refer to them as they're related to closed interval or open interval or half open, right? This is a half open. So the one side is closed, bracket is a closed, parentheses means open. So half open, half open. All of these half open, and this one is completely open. Okay, so half open, open, half open, half open. Okay, so that is how we apply, because in the next statement you can see it talks about the interval, functions is continuous on intervals as is closed, open, and so on and so forth. Okay. Let's look at the next one. The next one, we look at the picture. Okay, let's see if we can make our case, right? G, the function G is continuous in which interval? Between -3 and -2. Well, on the -3 side, excuse me, on the -3 side, obviously it's right continuous. On -2, it's not defined. So the interval will be open, will be closed open. Closed on the -3 side, open on the -2 side. Okay. And continue, we look at these intervals, right? From -2 to 1, from -2 to 1. At a -1, the function is undefined. So that continuity is going to be from -2 to -1. Both sides are open. Okay. And from 1 to 0, right? At 0 is left continuous. So G is continuous. On one side is open, closed. On the -1 side is open, closed on 0. Closed on 0. And from 0 to +1, let's look at this continuity. At 0 is left continuous, right? So G is continuous from 0 to 1, because at 1, there's neither left continuity nor right continuity. It's defined, there's no left continuity nor right continuity. And G is continuous from 1 to 3. On the one side, it should be open. On the 3 sides, it's going to be closed. Because at 3, the function is left continuous. Okay, I think that's all for left continuous, right continuous. So let's look at other statements. Okay, so we got these, look at these questions in your homework, right? How do we make use of it? We got some really interesting theorems, very, very useful theorems, right? They seem to be short and we go by them quickly, but they are profoundly useful. The first one is, it's about any continuous function. If f and g are continuous at a and c is a constant, then you add them, subtract them, you multiply them by a constant, you multiply the two functions, and you divide the two functions as long as the denominator is not 0, then adding, subtracting, multiplying, dividing, they're all continuous. This is a very, very powerful result. The second result, and it's called theorem number 5, I just quote that same number from the textbook, is any polynomial is continuous everywhere because the domain of polynomial is all real numbers. Any rational function is continuous wherever it is defined. That is, it is continuous in its domain. So we're going to use these theorems to make statements, okay? And the number 7 theorem saying the following types of functions are continuous at every number in their domain. Polynomial, we said it in the previous one, rational, root function means root 2, root 3, any roots. Trig functions, inverse trig functions, exponential logarithm functions. They are all continuous in their domain. So how do we use these? Last, number 4, is that if we use this continuity, right? If f is continuous, we can take the limit going through the limit, going across the function. You can take limit inside. We use this all the time. And the composition of two functions. If a function is continuous at a, and g is continuous, and f composite g is continuous, right? So let's see, we just gone over all of these interesting theorems. So let's see how we're going to use it on these homework questions. For example, the first one, A, right? F of x equals to x plus 2 times x raised to the power 3 to the power 4. Well, this is a polynomial, right? So how do we say it? Right? It's a use of definition of continuity and the properties of limit to show that the function is continuous at the given number A. Then this is what you can say. You say f is a polynomial, okay? And it is continuous in the entire domain, negative infinity to positive infinity. Okay, and negative 1, a equals to negative 1 is in its domain. Okay, therefore, thus, then you say f is continuous at negative 1. That's all you need to say. You're quoting the properties. We're quoting the properties. Okay? How about B? Right? So we just said A. How about B? B is a rational function. Right? What do we know about rational function? Rational function is continuous wherever it is defined. We just have to know that B is defined at 2, right? All we have to do. So in order to find out, then we just know that B, right? Let me write down G of T. What's the domain of G? Right? So we get C squared in the numerator plus 5t divided by 2t plus 1. And the number we're interested in is a equals to 2. Then you say the domain of G. What the domain of G is T not equals to negative half. sorry, negative half. In other words, G is defined everywhere, but negative half. 2 is in the domain, right? So you say 2 is in the domain of G. Then you say thus, right? Then you say thus, G is continuous at 2. That's all you have to say. Okay? Now, C, right? C, question number C. On this function, we got a function that P of V, right, equals to 2 times root. We have 3V squared plus 1. Oops, what I'm doing? Sorry. 3V squared plus 1. And A is 1. We have a theorem. It's that root functions are continuous in its domain. All we have to demonstrate that A equals to 1, 1 is in the domain of P. So what's the domain of P? What's the domain of this function? Well, for any input, right, because this is taking square root, but for each input, we're going to do V squared. So the domain is all real numbers. Okay, even though this is a root, the domain is all real numbers. And certainly 1 is in the domain, right? Then you say that P is continuous at 1. You see, that's how we use these theorems. And D is the same. And for root 3 functions, the function is defined everywhere. So for the case of F, the last one, okay, I'm not going to type it. The domain is all real numbers. So the same argument, Okay, so let's look at the next homework question, right? It says, use a definition of continuity and property and limits to show the function is continuous on the given interval. Right? Well, all we have to do is find the domain. What's the domain of function? F. What is the domain of function F? Right? It's x plus root of x minus 4. Right? And the interested interval is or closed, positive infinity. Well, the domain, we're going to use the root function is continuous, right? In its domain. So we just have to demonstrate the domain. The domain, this is a polynomial. The domain is all real numbers. The root function, the domain, we have to guarantee x minus 4 is at least 0, right? As a result, we get x is greater than or equals to positive 4. So x is greater than or equal to positive 4 is the domain that includes 4, right? And by the theorem, right, we have demonstrated the domain of function is x greater than equals to 4, and this is the sum of a polynomial and a root function. The sum of polynomial, right? F is a polynomial, G is a root function. Then therefore we use these theorems combined, so we can say F is indeed continuous on the close on this half open interval. Okay, and next one, G function. G function this time is a rational function, x minus 1 over 3x plus 4. The interval of interest is from negative infinity to -2, right? Once again, we're going to use these properties. Right? Rational function. We got a rational function. A rational function is continuous in its domain, right? So let's look at the domain of G. The domain of G is that x, right? We're going to set 3x plus 4 not equals to 0, right? As a result, we get x is not equal to -4/3. -4/3. -4/3 is actually larger than -2, right? So if you want to see better on this, okay, draw a picture for yourself. Draw a picture. And where is the -4/3? Say this is a -4/3. Okay, where will be -2? Well, -2 will be to the left of it. The interval of our interest is from -infinity to -2. And this is the number of, it's not in the domain, it cannot be in the domain. Therefore, this is what you're going to say. Okay, so here's the domain. You would say the interval is in the domain of G. It's part of the domain. Then you say thus G is, right? It's continuous in its interval. G is continuous in the given interval. So that's how you say it. Okay. I believe we did many of these examples. We did some of these examples before on discontinuity. All right, so let's move on to remove the discontinuity. Remove the discontinuity. Okay, removable discontinuity. I think we also did that. Okay, let's go on. I think we did that in the previous lesson. So let's continue. And number 17. Okay, this is also in your homework. Okay, so you're gonna do them in similar way that we did it in the previous examples. For example, capital F, the first question, right? The domain is all real numbers. It's a rational function, right? So it's a rational function, domain is all real numbers, therefore it's continuous on the entire number line. So we basically use these theorems. You see in the homework part, I bring these theorems together for you so that you can make your case. We can make your case. So you just learn to use these words, okay? And of course, you have to identify the interval. All right. And of course, that requires you to know the domain of all these different functions, okay? Let's see. Use continuity to evaluate the limit. Use continuity to evaluate the limit. This is when this theorem is used a lot. Okay. For example, A. Use continuity to evaluate limit. Okay. All right, the first one. How do we use continuity to evaluate the unit, the limit, right? So we got this limit here. X is approaching 2. Okay, the function is x multiply root of 20 minus x squared. Okay, so what point do we need to make? Well, the point we need to make, right? So here we're gonna use continuity to evaluate the limits. So what do we know about if a function is continuous at a point? Let's go back to the definition. If a function is continuous at a point, then the limit of the function when x approaching the point is a direct substitution. So here we basically say, can we do direct substitution? Okay, can we do direct substitution? So we have to make a case to say, well, the function, okay, this is our function, is it continuous at 2? And we have all these nice properties here, right? This looks like we have a polynomial and a root function. So we have one function multiply another function. So f is a polynomial, x, g is a root function. If both functions are continuous, then it is continuous at 2. Okay. Now the question is both functions continuous at 2? Well, polynomial x is continuous everywhere. The question is that it's root 20 minus x squared, is that continuous at 2, right? So this requires us to use all of these nice properties. You can use, some of these overlap, right? So let's find out the domain, right? So the only part of these two functions we have in question is 20 minus x squared in the square root. When we determine the domain, we have to do something about it. So we take 20 minus x squared, and we make sure it is greater than or equal to 0. That's the domain requirement. That is the domain requirement. And what else? With that, what do we get? Well, we get x squared less than or equals to 20, right? Or you just add x squared on both sides, okay? And you take square root on both sides. You take square root on both sides. The root 20 is root 4 times 5, 4 times 5. And root 4 times 5, that's 2 times root 5. Okay? And the root x squared is absolute value. It's absolute value of x. Right? And it is less than or equal to 2 times root 5. And what does that mean? It means that negative 2 times root 5 less than equals to x less than equal to 2 times. This is the domain. And this domain obviously contains 2, right? So you would say 2 is in the domain of the function. Which function? Well, the whole of it, right? Because the function, that domain is in the domain, right? Thus, the function is continuous at 2. Now we can use continuity to evaluate the limit. How do we do that? Well, we just do direct substitution. Replace x by 2, replace x by 2. What do we get? So that's 2 times root 20 minus 4, that's the root 16. Root 16 is 4, so the limit is 8. So you can see if we know a function is continuous at a certain point, evaluating its limit is just a direct substitution. That's what the definition of continuity is telling us. Okay, that's what we're being told. That's what we're being told. All right, so let's look at another situation. This time for B, okay, sine x, because in this case, you're going to be using sine composite with polynomial and sine. So you're using the continuity of 9, and they're continuous everywhere. So it's directly, so for B, because we know sine function is continuous everywhere in the domain of sine, which is a continuous function, right? So when we evaluate this limit, right? When x approaches pi, so don't be inhibited by this, right? So it's sine of x plus sine x, right? So this function is continuous everywhere. Okay? It's continuous in the entire number line. And certainly it is continuous at pi. It continues everywhere. Therefore, it is just a direct substitution because we used all these theorems to do it, right? So this is a pi, and this is a pi, and then you're going to evaluate. Sine pi is 0, right? So we get sine pi. Sine pi is 0, right? Pi plus 0 is 0. Sine pi is 0 once again. So that's B. How about C? C will be interesting to me because this will test us how much we know about logarithm. Okay, so I'm going to write down the limit, okay, as x approaching 1, and we have ln. This is a composite of functions, okay? So 5 minus x squared, 1 plus x. And once again, we have to demonstrate that 1 is in the domain of the function. Okay, so how do we determine the domain of this function? Okay, for ln x, the whole of it must be greater than 0. And what is more, the numerator must be greater than 0, and the denominator must be greater than 0. That's one way that we can We can test it. We can test it. Okay. So that's one way to do it. That's one way to do it. So from here, we will get x squared less than 5. Less than 5, sorry. Okay, so from here, right, from here, so all of these must be true. Okay, all of these must be true. And then we'll take square root on both sides, and we will end up with absolute value of x less than 5. So x between -5 to +5, right? On the other hand, right, so this is from 5 minus x squared must be positive. And then from here, x has to be what? X has to be larger than -1, right? X has to be larger than -1. If we combine these two, what do we get? Right? Because in this case, if we get -5 less than x less than 5, right? And on the other condition, logically, we have to make sure x is larger than -1. So combining these two, we will get the domain is x must be larger than -1 and less than 5. If both are guaranteed, okay, the quotient will be positive. The quotient will be positive. And +1 is well in the domain. +1 is well in the domain. So the domain now we get is from -1 to +5. Exclusive, not including -1. And obviously the function, right, which is a composition of log function and the rational function. Both are continuous in their domain, right? So we use these properties, logarithm function is continuous in the domain, rational function is continuous in the domain, and the quotient of two functions, continuous in the domain. The quotient is this piece, right? And logarithm function is continuous. We use multiple theorems at the same time, right? So we say, so by this time, you can say this function is continuous in that interval from -1 to +5. And 1 is part of it, okay? Thus, the function is continuous at 1, okay? And then we can just do direct substitution. So this limit, okay, so let me bring it down here. So this limit domain of the function. So let me just make sure I write it down properly because I'm going too fast. Sometimes I, type something wrong. So this limit is just a direct substitution, right? I'm going to plug in the 1, what do we get? We get ln, right? Because it's a continuous function at 1, right? Continuous at 1. So we're gonna do 5 minus 1 is a 4. 4 divided by 2 is a 2. ln 2. Done. Okay. last but not least, okay, not last but I'm going to do the D for you. I'm going to look at the D for you, okay? Because this is related to exponential function. So it's once again, it's a composition function. Okay, so x approaching 4, 3 to the power of root of x squared minus 2x minus 4. The point of interest is 4. So the question is, well, the exponential function is continuous everywhere, right? Exponential function, 3 to the power something is exponential. But the power is radical, is the square root. So we need to determine the domain of the square root, okay? The domain of the square root function, what would that be? Is 4 in it? That's the question. Is the 4 in it? Well, to determine whether 4 in it, there's actually an easier way to do it. You can just plug in the 4. If it is fall into the domain of the root, then you're fine. Here I'm going to show you another way to do this. Okay, so what do we do is that we're going to plug in the 4. We plug in the 4. And this is 16 minus 8. And we're getting root, right? What do we get? 16 minus 8 is 8. 8 minus 4 is 4, root 4. So that has already demonstrated, right? So you can say 4 is in the domain of this function because when we plug in, it is meaningful. So this can substitute the effort to find the domain, but I'm going to show you how to find the domain anyway, okay? So this would just be a direct substitution. So this would just be a direct substitution. You're going to put the 4 in place, right? So you're going to get 3 to the power 2, and that's going to be 9. So this question is done. This question is done. However, okay, in case you say, oh, I want to find I want to know the domain of the function. No problem. The domain, okay, the domain of this entire function. To determine the domain of the function. So we're trying to determine the domain of the function. So this has to be, okay, whatever underneath the root must be greater than or equal to 0. But in this situation, it's a little bit hard. It's a little bit hard to factor. Okay, so then what you do? What are we going to do? What I'm going to do is that I'm going to use b squared minus 4ac, that discriminant, minus 4ac. Okay, so what would that be? B is a negative 2 squared minus 4 times 1, right, AAC, and times negative 4. This is a positive 4, and this is a positive 15. So the whole thing, if you evaluate it, is a positive. It's a positive. Okay, so we can find the two roots. We can find the two roots. And that in that two roots, right? So you're gonna find so the root of this piece equals to 0 would be x equals to negative b, b is a negative 2, plus minus root 20 and 2a, 2 times 1, right? So we're getting root of 2 plus minus 2 times root 5 divided by 2. That will be equals to, because it's we have 3 2's, that will be reduced into root 5. Okay, so why do I need this number? Okay, so I will show you. I'm going to hopefully take this opportunity to review quadratic function a little bit for you. Okay, so this graph, this function corresponds to a quadratic function. Okay, and these two dots, we have a 1 minus root 5 and 1 plus root 5. Okay, so we have a 1 minus root 5. So I'm gonna plot dots for you, comma 0. So one is 1 minus, it's a red dot, and the other one is 1 plus. These two dots. And we want the function to be greater than or equal to 0. So this piece is greater than equals 0. This piece is greater than equals to 0. Okay, so I'm just showing you the curve. Then what will be the domain? I'm gonna make it 8. Okay. So what will be the domain? Of course, the domain will be these, right? So I'm gonna graph the domain for you. Will be 2 bars, right? So negative 10, 0, there, right? So we make it a line, solid, thick. And the other one, 1 plus root 5. You don't have to know how to use this software, so don't worry about it. Okay. So these are the domains. You can see positive 4 is well in that domain. Positive 4 is right there. Okay, so that's another way to see this. And of course, this requires you to review the knowledge about quadratic functions you have learned before, right? But that's what it is, right? And the easy way out, of course, is to just plug in and see if you get a meaningful number. For our input 4, do we get a meaningful number, which is positive 2, right? So we're good, we can directly substitute. But that feels like a little bit like a cheating, right? But anyway, you can do that, okay? Last but not least, there are a couple more examples here. I wish to go over some of it. Okay. It says, it shows that f is continuous from negative infinity to positive infinity. This is your homework question. How do we show that? How do we show that? ln x is well in its domain because the domain of ln x, x must be positive. For less than or equals to 1, it's 1 minus x squared. So obviously, as you can see, the only point of question for continuity, right, is 0.1. In other words, if we can show f of x is continuous at 1, then it's already continuous elsewhere. Okay, so in this case, for A, right, we just have to show, okay, so let me write it, let me type this. F of x is continuous on what interval? From 1 to infinity and, right, from greater than 1 because it's a log function. It's continuous in its domain. And the other interval is from negative infinity, which is a polynomial. Polynomial is continuous everywhere, to positive 1. So the only point in question is what? Is 1. Is A equals 1, if you like to say that, right? So we're going to observe if the function is continuous, right? So how do we prove a function is continuous? Definition, right? So we need to prove limit as x approaching 1, f of x is equal to f of 1. That's all we need to prove. So if this is in question, okay, this is in question. So how do we approach this? Right? Because the function assume different form from left and right, so we're going to look at the limit from left, smaller than 1, right? So that's going to be 1x approaching negative from 1 from smaller than, that's going to be 1 minus x squared. And that's a direct substitution. So that's 1 minus 1 squared. Sorry, 1 squared. So that's a 0. Limit from left, limit from right. Right? Approaching 1 from larger than 1, that's going to be, we're going to take the limit of the function of ln x, because that's the rule of the function when x approaching 1 from larger than 1. So this is the function we're looking at. So it's ln x. And ln x is a well continuous. Logarithm function is continuous in its domain. The domain of ln x is x greater than 0. And 1 is in its domain, so we just direct substitute. And that equals 0. Right? So left limit equals to 0, right limit equals 0. Then we can say the limit of the function, at 1 is equal to 0. But what is the function's value? F of 1. What is f of 1? F of 1, when x equals to 1, which function do we substitute? We're going to use the rule 1 minus x squared. That equals to 1 minus 1 squared. We use that rule. That equals 0. Right? Therefore, we have just demonstrated that they're the same. This is demonstrated. okay, is true because, so when you write it up, right, when you write it up, you want to have proper context. So then you say this is true, you can declare it is true because limit from left, limit from right, and all of these, you're going to make that statement, and closure, okay, conclusion, closure, okay, and thus, then you can say one more sentence, okay, f is continuous at 1. F is already continuous elsewhere, now it's continuous at 1, therefore, you can say f of x is continuous on what? On the entire number line. On the entire number line. That's it. Right? That's how you explain it. And of course, you can use your own words to put this conclusion later, right? Right before this piece, right? Right before this piece, you can change the orders, but it should be logically organized. Second one, look at this B. Okay, f of x equals sine x when x less than pi over 4. F of x equals cosine x when x is greater than equals to pi over 4. And this is the same situation. Okay, so f of x is continuous. Continuous where? From negative infinity to pi over 4. And the other interval, right, from pi over 4 to positive infinity. How do we know that? How do we know that? Well, trig function is continuous in its entire domain. Okay, sine function's domain is all real numbers. Less than pi over 4 is only part of it. Cosine function is continuous in its entire domain. So greater than or equals to pi over 4 is also part of it. So the only point in question is pi over 4, right? So we're going to do the same trick. We're going to do the same trick. So limits, right? When x approaching pi over 4, f of x, right? It's a limit from left. Limit from left. Then we're going to use sine function, right? So we're going to use sine function. And that's going to be direct substitution. Sine of pi over 4, sorry. Sine of pi over 4. And that's going to be root 2 over 2. If you forget this, and then you can look at, review your trigonometry on the top of module, okay? So let's look at the limit from right at pi over 4. This time is larger than pi over 4. And this limit, this time, we're going to substitute by cosine x. So once again, it's going to be cosine pi over 4, right? And it's also equals the same value. So, and the function's value at pi over 4, function's value, sorry, it should be pi over 4. Which function we should substitute it in? Cosine. Okay, so we just substitute in this. So by this time, you can say limit of the function when x approaching pi over 4, remove the size, is equal to the function's value at pi over 4. Okay, then you say, why don't you write root 2 over 2? You could, but the reason I like to write it this way because I wanted to quote the definition. I'm quoting the definition. The definition is that x approaching a, which is pi over 4 here, f of x, equals to f of a, f of pi over 4. So this way, I'm quoting the definition to make my case. Okay, so it's continuous. Therefore, you can say f is continuous at pi over 4. So, okay, and thus f is continuous everywhere, right? Because I already stated that from the beginning. Okay, from negative infinity to positive infinity. All right. Okay, so for these questions, number 20 in your homework, you use similar technique. Okay, left limit, right limit. If they're the same, you can just use it, right? If they're not the same, or if they're the same, then it's a limit exists. You're gonna use these definition of limit over and over again. Okay. Let me just do one example. Okay, because I don't want to make this too long. We already surpassed 1 hour. Okay, I'm gonna do the C. Okay, I'm gonna do the C here. And the instruction says, find the number at which f is discontinuous. At which of these numbers f is continuous from the right, from the left, or neither. Okay, so they asked us to demonstrate that. Okay, so this time I'm going to, we look at C. Okay, so f of x. The point in question, obviously, is 0 and positive 1. Okay, the points in questions are 0 and 1. So at 0, right, at 0, we're going to look at the limit when x approaching 0. Okay, smaller than 0. When approaching 0 from smaller than 0. I'm going to make the fonts a bit larger. Okay, approaching 0 from smaller than 0. And that limit, right? So you look at that piecewise function, that's x plus 2. So we're going to use x plus 2. That's the rule when x is less than 0. And that's a direct substitution. So 0 plus 2, and that equals to 2. And then we're going to look at the function, the limit of the function when x is approaching 0 from larger than 0. And this time, the rule of the function would be greater than or equal to 0. That's e to the power of x. So that's going to be a direct substitution, e to the power of 0 equals to 1. So obviously we have seen limit from left and right are not the same. There's a discontinuity. Right? So, but we're also going to look at the right continuous, left continuous, by the way. Okay, but first we answer the question where it is discontinuous. Okay, where it is discontinuous. So I'm going to have the whole question. We're doing C here. Okay, so first, and then you're going to say this limit from left is not equals to limit from right, right? And thus, the limit does not exist. The limit without size does not exist. So f is discontinuous at 0. Okay, so let's look at right continuity and left continuity. Okay, so that would require us to look at the function's value at 0. So what is f of 0? Right? When x equal to 0, we're going to use e to the power of 0 equals to 1. So now what do we see? The limit from right of 0 is equal to f of 0. Okay. I want you guys to look at the definition. Okay, look at the definition, right? X approaching 0 from larger than 0 equals to f of 0. Therefore, what do we say? We say f is right continuous at 0. It is discontinuous at 0, but f is right continuous at 0. Okay? Now, let's look at point 1. Okay, at point 1. Same trick. The same trick. Okay? So we're going to look at the limit from left of 1. And we're going to also look at the limit from left of 1, right of 1. Right? So let's look at the function. If we approach 1 from smaller than 1, and that the rule is e to the power x. And that's a direct substitution, e to the power of 1. That equals to e. When x is approaching 1 from larger than 1, the rule of the function is going to be 2 minus x. Okay, so 2 minus x. And we got 2 minus 1 equals 1. Obviously, the limit does not exist, right? So we have another point of discontinuity, but we also want to check out the left continuity, right continuity, isn't it? So let's evaluate f of 1. What is f of 1? For x equals to 1, we need to substitute into e to the power x. So e to the power of 1 equals to e. So now we can draw our conclusions. Okay, you can say f, right? We're going to use a definition here, right? This piece is equal to f of 1. Okay, left continuous. Okay, so you can say f is left continuous at 1. Okay, so that's about left, right, continuous, right? But we haven't said anything about whether it's discontinuous. Of course, we need to conclude it's discontinuous. So limit from left of 1 is not equal to the limit from right of 1. Okay? Thus, the limit at 1 does not exist. Does not exist. Okay? And then we say f is what? Is discontinuous at what? At 1. Oops. Is discontinuous at 1. So that's how you say it. That's how you say it. So you have two other examples to practice. And last but not least, okay, since we are here, so I guess this video is gonna be a bit longer, okay? But we're gonna do this. We're gonna look at 21, okay? 21 is asking us, saying, so what value of the constant c is the function continuous on the entire number line? Okay, on the entire number line. Obviously, this is the f function has two pieces. Both are polynomial. They're continuous everywhere. Because we made it into two pieces, the only point in question is 2. Right? The only point in question of 2 is 2. So we're going to take limit while x is approaching 2, f of x, right? Approaching 2 from smaller than and larger than. Okay, we want them to be equal. Okay, so when x is approaching 2 from smaller than, f of x should be substituted by the rule when x is less than 2. So that's going to be cx squared plus 2x. And that's a direct substitution, right? Cx squared plus 2x. I'm going to replace x by 2 and x by 2. And what do we get? We get 4c plus 4. 4c plus 4. That's the limit from left. Limit from right. And when x is larger than 2, because x approaching 2 from greater than 2, the rule of the function is x to the power 3, x raised to the power 3 minus cx. And that's a polynomial, and that's a direct substitution. We don't need the parentheses. So that's going to be 2x replaced by 2. So we got 8 minus 2c. Okay? To be okay. For f to be continuous at 2, right? These two must be the same. Limit from left must be equals to the right. Okay? This must be true. Okay? And what is f of 2? What is f of 2? The other thing is, what is f of 2? F of 2, we're going to substitute into x cubed minus cx. So it's going to be substituting into this. It's the same thing. Right? All we have to do is guarantee the left limit equal to right limit. That is 4c plus 4 equals to 8 minus 2c. So we're solving for c. Solving for c. What do we get? That's a simple solving linear equations, right? So what are we gonna do is we're gonna add 2c. So we get 6c equals to 12 and c equals to 2. C equals to 2. Oh, no, wait. I'm sorry. 4c minus 2c, that's 6c. -4 -4 on both sides, so this is it's gonna be a 4. So it's 2/3, sorry. 2/3. C equals 2/3, we'll make it. Okay, C equals to 2/3, we'll make it. Let's double check. Okay, we're finished after this question. Now let me double check. Okay. Left limit, cx squared 4c plus 4, 8 minus 2c, 4c plus 4 equals to 8 minus 2c, so that's going to be 6c, right? Because we're adding 2c on both sides, we get 6c, minus 4 on both sides, we get 4. And 4/6 is 2/3. All right, so that's all for this lesson. Thank you for watching. I'm sorry this is pretty long. I hope you can break it up. Okay, you can watch it by by pieces. You can watch it at different time, at different pieces. Thank you for watching.